Hello, y'all. Welcome to lesson 88 of my DP chemistry curriculum. Today we're going over reactivity 2.3.1. We're going to be talking about how a state of dynamic equilibrium is reached in a closed system when the rates of forward and backward reactions are equal. We'll describe the characteristics of physical and chemical systems at equilibrium. So with that said, let's just start with a physical equilibrium, the most basic and simple one. Now, a physical equilibrium is an equilibrium that exists between or during, between/during physical changes. One of the most common physical changes we think of are state of matter changes. So let's say we have a container, and in this container, we have a bunch of water. Now, if we seal this container off, we put a lid over it, so it is sealed. We have our water molecules inside moving around each other. This is a liquid, they slide around and move around. And then every once in a while, a molecule will pop off and evaporate and come into the air as a gas. At that same moment, too, while this is all happening, we might have a gas molecule that goes back down into the water. So we actually have two things that are happening. We have our H2O liquid phase evaporating and turning into our H2O gaseous phase. Simultaneously, while this is going on, we have our H2O gaseous phase condensing back into our H2O liquid phase. And so both of these reactions occur. Now, the way we would describe this in equilibrium is as such. H2O liquid is in equilibrium with H2O gas. And you'll notice we use this double-sided arrow. That is a very common thing when we mean equilibrium. This is our double arrow. What our double arrow signifies is it means that means the forward. So forward meaning to the right, that forward reaction. The forward process and the reverse process. The reverse process going backwards occur at the same rate. And what that means is equilibrium. That is the definition we started with at the top of the chapter. So what that means, once more, is our forward reaction is happening at the same rate as our reverse reaction. That is equilibrium. Now, one other word you often see thrown around is the word dynamic. Dynamic equilibrium specifically mean that both processes are occurring. We're always having changes. These particles are always in motion. They're always converting into liquid. The liquid is always converting into the gas. If this were a chemical reaction, the forward reaction is happening as well as the backwards reaction. They're both happening at the same time. That is what it means to be a dynamic equilibrium. One other thing about equilibrium, both physical equilibriums and chemical equilibriums, is they require what's called a closed system. We've talked about this when we've discussed endo and endothermic changes, when we talked about enthalpy, but to reiterate, a closed system is a system where only energy, and what I mean by that is not matter. So only energy can be exchanged between system and surroundings. So what that means is if we look back at our previous equilibrium, I could theoretically heat this up, put a fire under it, and we would likely have a lot more water particles evaporating. And we would still have some equilibrium where we have maybe more forward reaction and maybe less reverse reaction, but we'd still create an equilibrium because water is not leaving the container. It is stuck within it. The matter is contained, even though energy may not be. So equilibriums must be within a closed system. So required for equilibrium. All right. So a physical equilibrium, like we said, discusses a physical change such as a state change. But what we care more about and what we focus far more on is what we call chemical equilibriums. So chemical equilibriums are quite similar to physical equilibriums. They involve chemical changes. And as we mentioned before, in this equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, always. Now, we're going to go through chemical equilibriums with examples mostly, and one of the most common examples you will always see in any DP chemistry curriculum is called the Haber process. The reason this is so important is because this allowed us to produce ammonia, which is very important for crops. It's very important for different industrial usages. The production of ammonia is a very, very important process to the world we live in today. This is the synthesis of NH3, ammonia. So when we look at this equation, we have nitrogen gas reacts with 3 hydrogen gas to produce 2 ammonia molecules, also gaseous. We see that our reverse reaction is quite simply broken up into this, our forward reaction, while the reverse is the backward side. I should be a little clear with this. I should keep forward on top following the forward arrow, forward, and reverse. So reverse is a decomposition of ammonia, forward is synthesis of ammonia. This is the reaction that we're going to be focusing on for the next few examples. Now, we can look at this from a starting point. So when we first mix hydrogen gas and nitrogen gas in a reaction vessel, we can display with this graph. So we're going to look at this as a process of, and actually extend this a little bit. So this is our rate of reaction, and this is our time. When we take a look at this graph, we see that our forward reaction actually starts pretty fast. As our reaction starts, it's going to start at a very high rate. And the reason it starts at a high rate is because we have the highest concentration of reactants when we first put them in. As those reactants get used up, our rate will decrease. So we get a graph that looks kind of like that. I'm going to make it a little cleaner. And then it levels out. So this is our forward reaction. Forward. Now, our reverse reaction, on the other hand, is a little bit different. Because we start with no ammonia in our chamber, that means we start with no reactants according to the reverse, meaning our rate starts at 0. The more ammonia we produce, the more our reaction can proceed. And so our reverse reaction is the exact inverse of this. It's hard to see, but both of these appear at the same time. I'm going to try and draw them on top of each other so you can see. Then we'll zoom out. Our red representing our reverse reaction. These reaction rates, as they approach the same value, that is when we reach equilibrium. So that means our production of ammonia eventually becomes the same rate as the production of hydrogen and nitrogen from the decomposition of ammonia. So this is what it means to be in equilibrium. Those rates are equal. Now, one thing students get very confused with is what if we look at concentration? What happens to concentration? Well, what I'm actually going to do is end up copying the same graph, and I'll delete some stuff. I just want something approximately the same. And we're going to delete some aspects of this. We'll keep the time that we reach equilibrium the same. But other than that, we'll delete everything else. So now we're looking at concentration of our reactants in mole decimeter cube inverse, as well as concentration of products. If we look at hydrogen, we're going to start with the most hydrogen. The reason we know that's true is because our reaction has 3 moles of hydrogen to 1 mole of nitrogen producing 2 moles of ammonia. So we're going to start with about 3 times the amount of hydrogen as we would nitrogen. And that's going to decrease as our reaction progresses. We're going to reach a certain point, which is equilibrium, where it will remain constant. Because at equilibrium, if the forward and reverse reaction rates are equivalent, then that means that the amount of hydrogen in the chamber will remain constant. That is our H2. Nitrogen is going to start out at about 1/3 the amount. And then it's going to remain constant. Now, ammonia starts out with none. We start out without any ammonia in our reaction chamber. But as we produce it, that will also remain constant. So once we reach equilibrium, the concentrations remain constant. However, they are not equal. So at equilibrium, concentration is constant. I'll rewrite that. Is constant for reactants and products. It is not equal. So that is one of the key aspects. They are not equal. However, they are constant. The only thing that is equivalent at equilibrium is our rate. Rate is equivalent at equilibrium. So rate is equal to equilibrium. Reactants and product concentrations are not equal. They are just constant. They are no longer changing up or down. They are just remaining level. That is all you need to know about equilibrium right now for this section so far. I hope this helped and have a great day.